Pyrolysis of waste plastic and use of plastic oil as an alternate fuel in diesel engine. Abstract plastic is versatile, lightweight, moisture resistance strong, and relatively inexpensive. This inherent quality of the plastic made it an integral part of daily life, and as a result of which polymer products becoming massive scale worldwide. On an average 110 million tons of plastic is produced per year globally. Among this, India produces 14,088 kta thermoplastic in a year. About 70% of plastic products after use converted into waste in a short span, approximately 9.4 million tons per TPA generated in a country which 26,000 TPD. A proper plastic management system shall be developed to mitigate problems arising. 80% of plastic is recycled and remaining indispensable. These waste plastic is pyrolated to convert into useful liquid fuel. In the present study, an attempt is made to convert waste polyethylene milk pouches into oil in a batch reactor. The oil is characterized and found that suitable to use as a fuel in diesel engine. Due to favorable properties of plastic oil, it is mixed with diesel at 10%, 20%, and 30% by volume basics. This blend is used to run a single-cylinder diesel engine and to evaluate combustion, emission, and performances characteristics. The yield of plastic oil is higher for 460 OC, i.e. 784 grams/kg. It is found that break thermal efficiency of plastic oil blend with diesel is having higher than that of neat diesel. Further, as the percentage of plastic oil in the diesel increases, the break thermal efficiency also increases. However, emissions of the NOx for the blends are higher than that of neat diesel, and this attributes to oxygen molecule availability in plastic oil. Keywords: pyrolysis, waste plastics, plastic oil. 1. Introduction. Plastic is versatile, lightweight, flexible, moisture resistance, strong and relatively inexpensive. Those are attractive quality lead us around the world to such voracious appetite and over-consuming of plastic goods. Plastic products have become an integral part of daily life, as a result of which the polymer products massive scale worldwide. 1. Fig 1.1 shows cumulative global plastic production. In last 65 years the global plastic production increases to 7 million tons. On an average, production of plastic crosses 110 million tons per year globally. Its broad range of application in packing films, wrapping materials, shopping and garbage bag clothing tows, household and building materials, etc. Cumulative global plastics. Fig 1.1 Cumulative global plastics production. India, being second highest GDP and highest GDP growth rate among BRICS countries, has plus 7.1% growth in 2016. 2. This GDP growth has strong relation to petrochemical growth, that is polymer consumption growth. Agriculture, healthcare, solar energy, packing sector, defense, automobile production, and Make in India were initiative to attract investment to sustain GDP. Fig 1.2 a shows total export, and Fig 1.2 b shows total import during 2016 to 17. 13% of total import are resin plastic materials. About 14,088 kta is major production of thermoplastic production in India. Fig 1.3 shows major plant location of different polymers such as PS/Ps, LDPE, LLDPE, HDPE, PP, PET, PVC, etc. Fig 1.4 shows the total different polymer consumption in 2016 to 17, and consumption amounts to 15,500 kt. Average per capita consumption of plastic in India is 11 kgs against 109 kilograms of US, 65 kilograms of Europe, and 38 kilograms of China and 32 kilograms of Brazil. Higher per capita consumption of plastic is an indicative of developed countries. 3. A complication of mismanaged plastic waste in environment is a global growing concern. It is estimated that about 80 million metric tons of plastic waste were produced globally in 2015. 4. In India, it is estimated that approximate 70% of plastic making product converted into plastic waste in a short span. Approximately 9.4 million TPA plastic wastes generated in country, which amount to 26,000 TPD. Of this 60% is recycled, most of the informed sector. While recycling rate in India is considerably higher than the global average of 20%, there is still over 9,400 tons plastic waste which either landfills or ends up with polluting streams or groundwater resource. While some kinds of plastic do not decompose at all, other could take up 450 years to break down. 1. The recycling of a virgin plastic material can be done 2 to 3 times only because after very recycling, the plastic material deteriorate due to thermal pressure and its lifespan is reduced. Plastic waste management rules in 2016 were enforced from Government of India on March 18, 2016, in which fixes responsibility on local body, Gram Panchayat, manufacturer importer to reduce, reuse, recycle and recover the plastic waste. Under recycling depolymerization plastic to fuel, plasma pyrolysis technology is major. A new generation of conversion of technology specially designed to manage non-recyclable has been developed and commercial scale facilities that use pyrolysis technology to convert to plastic into oil and fuel are established in Europe and Asia. Pyrolysis is thermal decomposition of material at elevated temperature in an inert atmosphere. Pyrolysis has the benefit of transferring non-recyclable plastic waste into valuable compounded and creating a reliable source of alternative energy from an abundant, low-cost feedstock. In this project an attempt is made to identify low-cost local available feedstock, i.e. LDPE milk pouches. The estimated the quantity of pouches per day in our district milk pouches is 60,000. The total weight of milk waste pouches is turned to be around 920 kilograms per day. The batch reactor available in the laboratory is used to produce pyrolytic oil from milk pouches. Its characterization is carried out physiochemical, thermal properties of pyrolytic oil is compared with that of conversion fuel diesel. Further pyrolytic waste plastic oil is used as fuel to run a diesel engine. The combustion, emission, and performances characteristics were evaluated. 2.1 Summary on literature review. 80 million metric tons of plastic waste in the world per year, whereas the China alone produces the 25% of world plastic wastes. India produces approximately 9.4 million tons per annually of plastic waste, out of this 70% of plastic is discarded as waste. Nearly 60% of plastic waste is recycled and 20% are either landfills or ends up with polluting streams. Different types of plastics such as PE, LDPE, HDPE, PS etc. and their properties are studied. Different types of pyrolytic reactors are designed, tested and are in use. Batch and semi-batch reactor is simplest reactor and their working principle, construction, and variables affecting their operations were presented. The process parameters, physical and chemical properties of different plastics waste oil are studied. The favorable properties enable to use as fuel in boiler furnace, internal combustion engine etc. The recycling of a virgin plastic material can be done 2 to 3 times only because after very recycling, the plastic material deteriorate due to thermal pressure and its lifespan is reduced. 2.2 Gap analysis. Plastic is a bone because they are strong, corrosive resistant, and inexpensive. Per capita consumption of developed country is higher than that of developing countries such as India. But it is a bane because the plastics used in the daily life becomes a scrap within no time which creates environmental pollution related problems. All plastic waste cannot be recycled. Some of them are used for landfilling. After some years even the landfilled plastic will be speeded over the larger area and pollutes. In Kalburgi city milk will be supplied by Karnataka Milk Federation, KMF, Dud Pandhari from Maharashtra and from other local petty producers. KMF alone produces and sells 60,000 milk packets per day within no time plastic pouches convert into wastes. The estimated total weight of these LDPE plastics is equal to 920 kgs per day. The plastic wastes will be collected by the large number of waste pickers. 2.3 Objective of project. In this previous para it is observed that nearly 1 ton of plastic waste is produced from a milk producer's unit. Such milk packs can be collected and converted into useful commodity. The batch pyrolytic reactor available in the Laboratory of Mechanical Engineering Department may be used to convert these plastic wastes into useful pyrolytic oil. Further, this pyrolytic oil is used in internal combustion engine, boiler, and furnace as fuel. 2.4 Statement of the project. The statement of the project is as follows. Waste plastic pouches were collected from Karnataka Milk Federation KMF. This plastic pouches were cut short in small pieces. FTIR and TGA analysis of plastic collected from KMF were carried out. Based on the TGA analysis, the waste plastic yield at 430C, 460C, and 490C were experimentally determined. Thermophysical properties of waste plastic oil determined and compared with that of diesel. FTIR of the waste plastic oil is carried out at Ceramics and Cement Technology Department of our college. Waste plastic oil at 10%, 20%, and 30% of volume is blended with diesel. Further, these blends are used to run a single-cylinder diesel engine to evaluate combustion, emission, and performance characteristics. 2.5 Scope of the project. Output of the project gives a practical solution to mitigate problems arising by waste plastic at local. 3. Experimentation. 3.1 Introduction. In continuation with previous chapter, experimentation on pyrolysis of waste plastic pouches is explained in this chapter. The batch reactor available in the laboratory is reconditioned to work satisfactorily. An experiment is conducted on this batch reactor and yield of waste plastic oil is measured. Physiothermal properties of the waste plastic oil are determined. Further, this waste plastic oil with 10%, 20%, and 30% is blended with diesel on volume basis, and blends are used to run a diesel engine to evaluate the combustion, emission and performance characteristics. 3.2 Waste plastic pouches. Waste plastic pouches were collected from Karnataka Milk Federation unit of Kalburgi. It is observed that on an average 460,000 pouches are needed for packing of milk, curd, buttermilk etc. per day. The estimated milk waste plastic pouches are 920 kgs per month. The local available waste plastic pouches are considered for experimentation to find solution for disposal at local level. For every trail 1 kg of waste plastic pouches were taken and reduced to micro pieces. 3.3 Batch type reactor. A batch type reactor available in the laboratory is considered for pyrolysis of waste plastic. Fig 3.1 shows schematic flow diagram of waste plastic, and Fig 3.2 shows the photograph of pyrolytic reactor 31. The pyrolysis process is carried in a reactor where PID controller is used to control the temperature bricks. The reactor is made of mild steel, and to minimize heat losses it is insulated with refractory. The length of reactor is 56 cm with the internal and external diameter of 21 and 56 cm respectively. The length of the condenser is 140 cm, having inner and outer diameter of pipe is 1.905 and 3.81 cm. The inner pipe is made up of galvanized iron, Gi, and outer with copper material. The vapor residence time in the reactor is maintained around 10 seconds. Water is used to condense the vapor coming out of reactor. The nichrome coil having capacity of 3 kW is used to heat the reactor, and J-type thermocouple having range of -99 to 870 C is used to measure the temperature of biomass 31. IMG_20190815_1801004_01. Fig 3.1 Schematic diagram of waste plastic pyrolytic reactor. IMG_20190728_131039. Fig 3.2 Photograph of pyrolytic reactor. 3.4 Pyrolysis. Fourier transforms infrared spectroscopy, FTIR, analysis and thermogravimetric analysis, TGA, is carried out at Kelvin Labs Hyderabad. Fig 3.3 shows the FTIR analysis of plastic waste considered in experimentation. It is observed that the waste milk pouches considered for the experimentation is polyethylene, i.e. LDPE, low-density polyethylene. Fig 3.4 shows the TGA analysis of waste milk pouch plastic. From analysis it is observed that LDPE content is 98.9%, volatile material is 0.2% and ash content is 0.9%. Converting the plastic into oil initiate at 280 C and likely to end by 520 C. Based on the TGA analysis for each test 1 kg of waste plastic is considered for pyrolysis. The yield of 1 kg of waste plastic is determined at 3 different temperature, i.e. 430 C, 460 C, and 490 C respectively. The oil collected and ash left in the reactor is measured and difference of these two from 1 kg gives mass of gas released. 3.5 D diesel engine. The plastic oil collected during the pyrolysis is characterized. This plastic oil is blended with diesel at 10%, 20%, and 30% on volume basis with diesel and blend is prepared. These blend were used as fuel for running a diesel engine. The combustion, emission, and performances characteristics of diesel engine with these blends are evaluated and result are compared with that of neat diesel. The schematic diagram and photograph of the diesel engine shown in Fig 3.4 and Fig 3.5. The specification of the engine used for testing is shown in the table 3.1. For results and discussion. 4.1 Introduction. This chapter deals with experimental outcome of using waste plastic oil. FTIR and TGA analysis of waste plastic oil is presented. The output of the batch reactor is experimentally determined and waste plastic oil characterization is carried out and presented. Further different blends of plastic oil with diesel prepared. These blends are tested on single-cylinder diesel engine to evaluate the combustion, emission, and performance characteristics and compared with that of net diesel on single-cylinder diesel engine and presented. 4.2 Variation of yield of plastic oil at different temperature. The sample collected for the pyrolysis oil is 1 kg. The sample of plastic under test is subjected to the pyrolysis at 430 C, 460 C, and 490 C respectively. The output of oil, char, and vapor, by difference, for pyrolytic process are presented in the table 4.1. The variation of plastic oil output with respective to the different pyrolytic temperature are shown in Fig 4.1. It is observed that these temperatures considerable amount of plastic oil has been collected. The maximum output of the plastic oil 784 grams/kg is collected at 460 C. It is further observed that the quantity collected reduces with increase in temperature and found minimum 0.2% at 490 C. 4.3 FTIR Analysis of plastic oil. The Fourier transform infrared spectroscopy, FTIR, of plastic oil is carried out in the Ceramic and Cement Technology Lab and their result are presented in the Fig 4.2. Plastic oil sample is subjected to the FTIR analysis to find out chemical combination of sample. The relative absorbance wave number obtained from FTIR analysis is shown in Fig 4.2. It can be seen that there are 8 major peaks. Using characteristics infrared absorption band of functional group, the class of compounds, their intensity, and nature of bonds determined. Table 4.2 shows detail of compound and their characteristics pertaining to peaks observed in the FTIR analysis. Sample of the plastic oil consists of aromatic, alkenes, alkane and alkyls, carboxylic acids. Major peak assigns to the carboxylic acid. It has class of organic compound in which a carbon atom is bonded to an oxygen atom by a double bond and to a hydroxyl group, O, by a single bond. Alkane is a compound having single bonded open cycle saturated hydrocarbon molecules, for larger molecules exits. Example CH4, methane, C2H6, ethane, C3H8, N-octane, C8H18, isooctane. Alkenes compounds are open-chain hydrocarbon containing a double bond and they unsaturated. Example C2H4, ethane, C3H6, propylene, C4H8, butane, etc. Benzene and its derivates were called aromatic compounds, which are having a cyclic structure with alternatively single-band double bonds. Plastic oil is similar to the diesel in structure. However, additional hydroxyl group, O, is bonded. It means oxygen molecules are inbuilt and available readily during combustion. 4.4 Properties of plastic oil and diesel. The density, kinematic viscosity, calorific value, flash and fire point of plastic oil and diesel used under test were carried out in the laboratory as per these as standard. These values are presented in the table 4.3. It is observed that density and calorific value of plastic oil is lower and kinematic viscosity is higher than that of diesel. The density, calorific value, and viscosity of plastic oil are 82.9%, 80.88% and 184.65% of that of the pure diesel. The viscosity of plastic oil, though it is 184.65% of that of diesel, it has sufficient value to obtain better spare and penetration. Flash and fire point of plastic oil are well comparable with that of diesel. 4.5 Combustion characteristics. Variation of cylinder pressure with crank angle. Fig 4.3 shows the variation of cylinder pressure with respective crank angle at maximum load. It can be observed that the trend of pressure variation for the fuel under the test is similar. Pressure of D70P30 is higher, followed by D80P20, D90P10, and D100 respectively. Fig 4.4 shows difference of peak cylinder pressure at maximum load for all the fuel under the test. From 20% to 100% of load, the cylinder pressure of the D70P30 is higher compared to other fuels. However, difference of pressure between D90P10, D80P20 is almost same and little higher than that of D100. At highest load peak cylinder pressure, D70P30 is 63.47 billion Argentine pesos against 62.08, 61.33, and 60.27 billion Argentine pesos for D80P20, D90P10 and D100 respectively. Variation of net heat release rate with crank angle. Fig 4.5 shows variation of net heat release rate with crank angle at full load. Rate of heat release for D70P30 is higher compared to other fuels under the test. Clearly, it indicates that increase in percentage of plastic oil and diesel improved the combustion quality and higher pressure in cylinder. Fig 4.3. 4.6 Emission characteristics. Variation of smoke with respective to the brake power. Fig 4.6 shows variation of smoke with brake power. Smoke emission increases as the load increases for all the fuels under test. It is observed that smoke of diesel D90P10, D100 is almost same. However, by increase in percentage of plastic oil and blend proportionality, smoke emission increases. At maximum load, smoke emission of D70P30 is 92.9% opacity against 98.3%, 97%, 98.4% opacity that of D100, D90P10, D80P20 respectively. As the load increases, the quantity of fuel injected in the cylinder increases. Because of this, mixture becomes rich mixture and smoke emission increases. Variation of carbon monoxide with brake power. Fig 4.7 shows variation of carbon monoxide in percentage with brake power in kilowatt. Up to 80% of load CO emission of all the fuel under test decreases and at full load increase. At full load, smoke emission D70P30 is 0.77 against 0.76, 0.51, and 0.51 of D80P20, D90P10 and D100 respectively. At maximum load, as the mixture becomes rich, due to this some of the carbons are not converted into carbon dioxide. Variation of unburnt hydrocarbon with brake power. Fig 4.8 shows variation of unburnt hydrocarbon with brake power. It is observed that unburnt hydrocarbon increases as the load increases for all the fuel under test. As the percentage of plastic oil in the blend increases, the unburnt hydrocarbon also increases. At maximum load, the unburnt hydrocarbon is 106, 95, 115 and 118 part per million, ppm, for D100, D90P10, D80P20, and D70P30. As already mentioned, that as the load increases, the quantity of fuel injected increases, which makes fuel-rich mixture. Due to quenching and Krives flows, the unburnt hydrocarbon exhaust increases. Variation of oxides of nitrogen with respective to the break power. Fig 4.9 shows the variation of oxides of nitrogen with break power. NOx emission increases with increases in the load. Higher the percentage of plastic oil in the blend leads to the higher NOx emission. Complete combustion of the plastic oil blends leads to higher exhaust gas temperature. Fig 4.10. Plastic oil consists of oxygen molecules in its structure in addition to carbon and hydrogen. The oxygen readily available for combustion where a part of this oxygen reacts with nitrogen forms NOx emission increases. Further, as the load increases, more amount of oil is injected and mixture becomes rich, so it emits higher NOx. 4.7 Performance characteristics. Variation of brake thermal efficiency with brake power. Fig 4.11 shows the variation of brake thermal efficiency with brake power. The maximum brake thermal efficiency occurs at 80% of the load. As the load increases, the quantity of fuel injected into the cylinder also increases, which leads to higher power development. The blends having D70P30 is having higher brake thermal efficiency at all load, followed by D80P20, D90P10, and D100. The maximum efficiency of D70P30 is 28.03% against 27.03%, 27.07%, and 25.68% of D80P20, D90P10 and D100 respectively. Variation of brake-specific fuel consumption and brake-specific energy consumption with brake power. Fig 4.12 shows variation of brake-specific fuel consumption, BSFC, with brake power, and Fig 4.13 shows the variation of brake-specific energy consumption, BSEC, with brake power respectively. BSFC curve is reverse of brake thermal efficiency. The minimum BSFC of D70P30, D80P20, D90P10, and D100 are 0.33, 0.27, 0.32 and 0.33 kg/kWh. However, BSEC is better tool to measure the performance of the engine. It is found that minimum BSEC of D70P30, D80P20, D90P10, and D100 are respectively 10,416, 11,036, 14,456 and 13,600 kg/kWh respectively. Better combustion, higher heat release and increase in the cylinder pressure leads to better performance among all the oils tested. D70P30 are better compared to other fuels. 5 Conclusions. Following are the conclusion drawn from the experiment/project. Higher plastic oil yield occurs at 460 OC, which equal to 784 grams/kg. Plastic oil consists of additional oxygen molecules, hydroxyl group, in its structure. Density, calorific value for plastic oil is lower and viscosity is higher than that of diesel. Flash and fire point of plastic oil are well comparable with diesel. Brake thermal efficiency is higher than of pure diesel. As the percent of plastic oil increases in the blend, the performance of the engine is better. Smoke, unburnt hydrocarbon, and NOx emission increases with percent of plastic oil in the blends.